The good news is it's only going to go 10 minutes, and then I have to do it again, and after that it'll go forever. All right, so this is what is this anyway? Digital circuits. Oh, good. Is it digital circuit 1? Oh, it's digital circuits 1. We don't have a digital circuits 2, but that's okay. We're in chapter 1. Did I spell chapter right? Okay, so we're in chapter 1, and we're going to start with section 1. And we're going to ask the question, what is the difference between something that's analog and something that is digital? I spelled digital, D-I-G-I-T-A, all that. Oh, where'd it go? Just wonderful. Wonderful spelling of the word digital. Okay, so I'm gonna demonstrate an analog signal first. So here's my analog signal. It is continuous. It can be anywhere on that line. It can be at a half and a quarter and a 3/8 and a 7/16, and there's a million, billion, zillion different places it could be because it's analog. A digital circuit doesn't have that. A digital circuit can only be at one place or another. So I can be at a 1, well, we'll call that a 0. I can be at a 0 or a 1 or a 2 or a 3 or a 4 or a 5, but I can't be at a 4.5. Okay, so that's the difference between an analog circuit. The clock over there, if you look in the back of the room, that clock is digital. It's clicking a second at a time. That line isn't sweeping through the second, so it could be anywhere during the second. It's only a second at a time. It's a digital thing. My computer here is a digital thing. It only knows ones and zeros. When you take your calculator and add 2 and 3 and get a 7, it doesn't know 2, it doesn't know 3, it doesn't know 7. It only knows 0 and 1, on and off. So a digital circuit is on, a digital circuit is off. Okay, so that means we've got to pause this for a moment. Control F11. Or is it Shift F11? Shift F11. Control Shift. Boom. Okay, sometimes we get more fancy than just on and off, and we say it's true or it's false. So we substitute one single syllable word on for a single syllable word true, and another single syllable word off by another single one, meaning saying false. But true and false, on and off, are the same thing. Sometimes we go and say true, so A is going to be true, and then we go A naught, and we put a bar above it, that's going to be false. So we can go and do it that way. So that's digital. I think that may have been section 1.1 and 1.2 both. Yeah, I guess so. We got pictures of watches here and all kinds of cool stuff. All right. So now we're going to worry about something cool called decimal numbers, base 10. All right, well, why not? So section 1.3, and we're going to talk about base 10. When was the last time you used base 10 for anything? On the way here in your car looking at your speedometer? Yeah, okay, right, exactly. Okay, let's ask the question. When Isaac Newton was alive, did he use base 10? Isaac Newton. There we go. Answer yes. How about Henry VIII? Did Henry VIII use base 10, King of England? Henry VIII. Yes, he did. How about 1,100 years ago? So it's 1,000 AD. Are we using base 10 anywhere? Yes, we are. Okay. How about 700 AD? Are we using base 10 anywhere? Yeah, okay. Well, that's it. So this is base 10. Why don't we add over here base 60? Base 60? Are you kidding me? Anybody use base 60?
I honestly don't know what base is.
Oh, that's good. You know what a tenor is?
What?
You know what a tenor is?
No.
You don't know what? How about a soprano or an alto? You know what they are?
Altoid.
Huh? Oh, that's a different bass. That's BASS, right? Okay. Yeah. Well, anyway, turn around and look at your clock. There are 60 seconds in a minute. There are 60 minutes in an hour. Base 60 is what your clock is based on. It has, in the original format, it had 60 digits, 1 to 60.
So it's base 10.
Yeah. Base 10 are numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are the numbers that make up base 10. It's what you've done your entire life, except that the math department didn't call it that. Because when Sputnik went up into orbit, my math department had to teach us base 10 and base 8 and base 2 and all the other bases. And they haven't done that in the high schools for a very long time now. All right, so we're going to have to ask the same question about this base 60 time, the clock, right? Did Isaac Newton have 60 seconds in his minute?
Yes.
Yeah. How about Henry VIII? Did he have 60 seconds in his minute? How about 1,000 AD?
Yes.
Yes. How about 700 AD? All right, so those guys had 60 seconds in their minute and 60 minutes in their hour. Okay, how about we go to 600 AD? Is anybody using base 10?
Yeah.
The answer is no. No one is.
What was the question?
Base 60, yes. Base 10. Is anybody using base 10, the numbering system we commonly use today in our currency and everything we think about? Was it being used at 600 AD by anybody? And the answer is no. We had Roman numerals, but we didn't have base 10. It wasn't until 650 AD that the Moors in northern Africa came up with this idea of having base 10. And it was such a brilliant idea that everybody accepted it. I mean, why haven't we been doing, why, I mean, 10 plus 10 is 20. Why haven't we been doing that? Why have we been doing this? I mean, this is garbage. Trying to add in Roman numerals, right? I mean, how can we, here we go, 20 plus 20, we'll go up again. Okay, Roman numerals, let's see, XX plus XX is XL. So that's 20 plus 20 is 40. There, brilliant. Now, and how am I going to multiply? How am I going to multiply? How could you have a science or anything at all? You can't multiply, you can't divide in Roman numerals. How about 1,000 years BC, before Christ? Well, we don't have base 10. Do we have base 60? Is there 60 minutes in the hour? Yes, there is. Yeah. How about 2,000 BC?
How could you have a base 60 if you don't even know what a freaking watch looks like?
You did. They did.
No.
But yet they had, yeah. Now, the issue that you have that you're dealing with is one of a very interesting one, and that is, who do we teach the math to? Okay, and that's what you're dealing with now. So in 2000 BC, this base 60 math, where they multiplied, added, subtracted, and divided using base 60 different symbols for their numbers, and they used it in their clocks, and they used it in a circle application, 360 degrees in a circle. That was only being taught to a very small portion of the population. So the priests were teaching that to 0.01% of the population. It wasn't like I was trying to teach everybody that. Whereas the arithmetic we try to teach you from kindergarten on, we're trying to teach that to the whole population. We want everyone to be able to balance their checkbook. We want everybody to be able to tell time. We want everybody to know how many miles per gallon they're getting in their car and what that means. Okay, so that's the part that you're dealing with. Same thing if you look back at India, 1,000 years ago, they had math that was far superior to our math that we had 100 years ago. But they weren't teaching it to the whole population. They're only teaching it to the Brennan class, the class of people at the very top of the food chain. And so that no society except the United States, when did we do it? 1828. In 1828, we were the first society to have a public high school. So before 1828, we had private high schools that you could go to, and we had universities you could go to. But in 1828, Boston and New York City both went and, if I could spell Boston, both started public high schools for everybody. And that's what got us to where we are today. The idea that we can educate the whole masses and have a society that's increasing in knowledge exponentially, really, for a long period of time. All right, so back to base 10. In base 10, we have the units place, also known place. If I could spell place, P-L-A-C-E. We call it the ones place, and then we have the tens place, and the 100ths place, and the 1,000th place. And we look at that and we say, well, this is 10 raised to the 0 power, 10 to the 0. Anything raised to the 0 power is 1. So 10 to the 0 power. This is 10 to the first. That's 10 squared. This is 10 cubed. And now if I have 3, 2, 4, 5, if I could make a 4, 3, 2, 4, 5, then that's 3,245, but it means 3 times 10 to the cubed plus 2 times 10 squared plus 4 times 10 to the first plus 5 times 10 to the 0. And now that's what base 10 is talking about. Each of these digits have some weighted meaning associated with it. Each of them, as I go to the left, is 10 times more than the one to the right of it. I can go 1, 2, 3.4, 5, 6. I'm going to quit making 4s. All right, so this is the 100ths place. 10 squared. This is the tens place. 10 to the first. This is the units place. 10 to the 0. That's the 10th place, 10 to the minus 1. That's the 100th place, 10 to the minus 2. That's the 1000th place, 10 to the minus 3. And we all have a common experience with our algebra and our math coming through high school, coming through third grade or whatever. What do you guys make it up to anyway, second grade? Anyway, somewhere around there, right? And we understand that that's what those numbers mean to us. All right. So, what are we going to do next? We're going to do base 2. In base 2, I have 2 numbers. I have 1 and 0. That's all I'm allowed. Base 10, I had 10 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Speaking of which, yeah. Let's look, before we look at this, let's look at this village. I got this house here. It belongs to Sam. And I got this house over here, and it belongs to George. And then I got this house over here, and it belongs to Linda. And it's 1 AD is the time frame. Okay, so it's 1 AD. And I'm going to ask the question, how many houses are there?
Looks like 3 to me.
Okay, so we'll ask the question again. It's 1900 in the United States of America. How many houses are there? 3. Okay, so there's 3. In 1900, there would be 3 houses. At the time of Christ, there aren't 3 houses. They had no way to express that idea. There's Sam's house, there's George's house, there's Linda's house, but they had no language to express the idea of 3 houses.
So the number language, that's what you think.
Yeah, exactly. So you read in your Bible, and there's this army that has 100,000 men. Wait a minute, the number 100,000 wasn't even possible until 2,000 years after that passage was written. What is it really saying? It's really saying there's a whole lot of guys in that army. No one actually counted them. Okay, there's a huge amount of people over there. Okay, and the army was very big. And to express that in the English language, you say, well, there's 100,000 of them because that's a pretty big number. Okay. All right, back to base 2. So for base 2, we have 1s and we have 0s. That's all we got. We have the units place. Right there, there's the units place. And it's 2 to the 0, which is a 1. And then we have the 2's place. 2's to the first. Those are 2's. And then we have the 4's place, 2 squared. We'll put a 4 there. And then we have the 8's place, 2 cubed. And then we have the 16th place, 2 to the 4th. And we have the 32nd's place, 32nd, 2 to the 5th. All right. And we can go further. We can go 64, 2 to the 6th, and then we could go 128, 2 to the 7th, and then we ran out of room, so we won't go any further than that. So now I got this base 2 number 101110, and I want to know what is that number in base 10? That's what I want to know. All right, so I change color, and I look there, and I have 0 1s. I've got a 2. I've got a 4. I've got a 8, I have no 16s, and I have a 32. So I add them together, 46. So 101110 base 2 is 46 base 10. And you say, well, gee, that means the digital circuit class is just another way to add numbers together. I say, yeah, that's about it. Yeah, pretty much. All right.
What's the 10?
That's base 10.
Basic.
Yeah, that's a lowercase 10 would indicate that number's in base 10. Because we normally don't put it there, it's normally not there. So when I talk about dollars, I don't put it there. When I talk about anything, I don't put it there, except in a digital circuit class where I might be in a different base, so now I've got to put a 10 there to say it's base 10. All right. Now we're going to go the other way. I got 3,542. And I want that to go to base 2. How am I going to do that? It's too big, right? Take me too long? Okay, we'll make it smaller. We'll take 354. And we want to change that to base 2. Several ways I can do that. First way is I can just take out my calculator and tell it to do it. I told you like this calculator, right? So, I go and I turn my calculator on. Okay, so my calculator's on. So I got 354. And I'm going to go in second function base. I'm going to send it to binary. Boom. And so the correct answer is 10110010 base 2. So so my calculator will just do it for me. I really don't have to. So that's why I want you to buy this calculator. So before the first chapter test, so that all you're doing is just telling your calculator to do it, does it for you, and everybody's happy. Okay, well, I don't have my calculator, so I can't do that. I got to do it manually. Okay, so I've got 3, 5, 4. Okay, I'm going to divide that by 2, and I've got 1, 1, 4, 1, 7, 177,
177.
177, and I got a remainder of 0. Okay, I'm going to divide that by 2, and I've got 2 goes into 17 8 times, 8, 8,
87, yeah.
remainder 1. Right, 8, 8, remainder 1. And then I'm going to divide by 2. I'm going to get 44, remainder 0. And then I'm going to divide by 2 again. I'm going to get 22, remainder 0. I'm going to divide by 2 again. And I'm going to get 11, remainder 0. I'm going to divide by 2 again. And I get 5, remainder 1. I'm going to divide by 2 again, and I'm going to get 2, remainder 1. I'm going to divide by 2 again, I'm going to get a 1, remainder 0. And then I'm going to divide by 2 again, I'm going to get a 0, remainder 1. And then I'm going to write down my answer, 1, 0, 1, 1, 0, 0, 0, 1, 0.
That's so cool.
Right here, 0, 1, 0, 1, 1, 0, 0, 1. And can anybody not divide by 2 in the room? Show of hands, be honest. Okay, is that the same number I had before? That's the same number I had before.
Yeah.
So I changed from base 10 to base 2 by dividing the number by 2, remembering what the remainder is until I get done, until I have nothing left, and then I have the number base 2. Okay, one more way. Okay, so I like my calculator way best, by the way. My second favorite way is what I just showed you. Okay, my third favorite way, what is it? 3, 5, 4. Okay, so I got this number. Units place, the 2s, the 4s. I like pictures. 8. Do you guys like pictures?
That's part of the
16. I got colored pens in my pocket with 8 different colors of ink. Not today, though. I put the same ones in my pocket. Bummer. Only 4 different colors of ink. 32, 64. I'm multiplying by 2 if anybody was wondering. 128, 256, 512. 3, 5, 4. Do I have any 512s? No. Do I have a 256? Yes, I do. 256. I'm subtracting. 8, 9, 8, 9. Yeah. Do I have any 128s? No, no 128s. Do I have a 64? Yes, I do. Minus 64. 34. Do I have a 32? Yes, I do. Minus 32 means I got a 2 left. 0, 0, 0, 1, 0. Is that the same number I had before? Okay, so there's 3 different ways that I know of. My favorite, make your calculator do it. You got to have it. You got to practice on it to make it do it. Divide by 2, or write down the weights of the binary number until you get higher than what you're looking for, and then fill in the blanks. Okay? Good enough? All right. We'll move on. I think we have to go the other way. Well, we already did the other way. Okay, so that's 5-1. We did decimal to binary. Okay, decimal to binary. We just did it. We did it 3 different ways. Now we're in chapter 1, section 1.6. Now, binary ones and zeros is the way we programmed computers in 1940 and in 1950. And I have a computer in the lab that's the first home computer, and you programmed it using ones and zeros. You had a bunch of switches across it, and it was either a 1 or a 0, and that's the way it entered the program code. Well, it is slightly inconvenient to have 1,000 people around trying to enter codes, ones and zeros, right? So the first thing we did was we went to a base called octal, and octal means 8, right? So base 8. And now in base 8 we have a 0, a 1, a 2, a 3, a 4, a 5, a 6, and a 7. Okay, so if I go and I'm going to make a number thing here. 0, 1, this is base 10. 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? And if I was in base 2, I would have a 0, a 1, a 1, 0, a 1, 1, a 1, 0, 0, a 1, 0, 1, a 1, 1, 0, 1, 1, 1, and 1, 0, 0, 0. So that would be my base 2 representation of the numbers. If I was an octal, base 8, I'd have 0, 1, 2, 3, 4, 5, 6, 7, 1, 0. Notice that I didn't say 10, I said 1, 0, because I'm in base 8. So it wouldn't make any sense to say 10 in base 8. 1, 0 is 8. Confusing enough? All right, so now I've got a system that's like that, and now I'm going to have to go and look at what we're doing. All right, we'll look at what we're doing. So I got the units place. I've got the 8 to the 1's place. Units place is 8 to the 0. I got the 8 squared place, 64. I got the 8 cubed place. Anybody know what 8 cubed is? 512? All right, well, we'll believe you. No, we won't. 8 times 8 times 8. Yep, 512, that's right. So that's a 512's place. And then we've got the 8 to the 4th place, times 8 again. 4,096. All right, well, that's cool. Hope I remember that long enough. All right, so I've got a number, 354 in base 10, and I want to change that to octal, base 8. That's what I want to do. So I take up my calculator. I put in a 354. Second function base, and I'm going to change to octal, boom, and it tells me the answer is 542 in base 8. So that's my favorite way of changing from base 10 to base 8 is just using my calculator and do it. Okay. Now, if I do a similar thing I did to base 2, and I took 354, and I divided this by 8. Let's see. 8 goes into 35 4 times. 8 goes into 34 4 times with a remainder of 2. I divide that by 8. 8 goes into 44 5 times with a remainder of 4. And 8 goes into 5 0 times with a remainder of 5. There's my 542, the same 542 I have there. Okay, and you say, Cordoville, you're pulling my leg. You have to be pulling my leg because you left it there. You can look at it. You don't have to do the divide. This is garbage, you know. Anyway, but no, it worked. I didn't look. Good thing there's not a stack of Bibles here. All right. The other thing I can do is do what we did before and say, well, this is the units place. This is the 8's place. That's the 64th place. This is the 512 place. And I've got 3, 5, 4. I obviously have 0 of those, and I have 5 of those, and I have 4 of these, and I have 2 of those. Yeah, obviously. That's not so obvious, is it? But it is because I already did it. So that would not be my favorite way to do it. I wouldn't want to do that at all. So now we have the issue of we're in base 8, and I want to go the other way. All right, so I've got 1, 3, 4, base 8, and I want to know what it is base 10. So I take my calculator, and let's see, second function bases, type. All right, that's not the right type. I don't want that type. All right, so 1, 3, 4, second function, bases, type, octal. So now I have an octal number, second function, bases, no, second function, bases, and I want to be in decimal. Boom. All right, 92. Is that really 92? Oh, we don't know yet. Calculator says that it's 92. All right. I look at this and I say, well, that's a 4. That's a 3 times 8, which is a 24. 24. And that's the 64 spot, 64. I add them together, 4, 4, 4, 2, 1 to carry 9. Same number.
How do you get the 64?
Well, in base 8, I have the 1's place, the 8's place, and the 64th place. 8 squared. 8 to the first. 8 to the 0. So that's how I do that. Okay. And I'm only going to go to, not going to go much further. We'll do, so now I've got 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1. Maybe. So that's what I got. And I want to change this to octal. So I got that. I'm going to change it to octal. And I say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Bummer. My calculator won't do it. My calculator will only take 10 of them, and I've got 13 of them. Oh, woe is me. Okay. But if I look at the table I had before of the tens and the binary and the octal, I see that I have 0, 0, 0, 1, 1, 1, 2, 1, 0, 2, 3, 1, 1, 3, 4, 1, 0, 0, 4, 5, 1, 0, 1, 5, 6, 1, 1, 0, 6, 7, 1, 1, 1 for a 7. And I say to myself, self, I see a pattern. 1, 2, 3. 1, 2, 3. 1, 2, 3. Can I count to 3? 1, 2, 3. So in octal, this number is going to be 1, 2, 6, 7, 1. That's all I did. I took the. Yeah. Well, see, when I group these guys in threes, I end up with 0, 0, 1. 0, 0, 1 binary in octal is 1. 1, 1, 1 in octal is 7.
How did you get all the stuff in the purple?
Well, inside, I'm grouping them 3 at a time, is all I'm doing. I'm grouping them 3 at a time, because what's this place? This is the units place, that's the 2's, that's the 4's. What's this place? This is the units place. Okay, this is the 8, the 16, and the 32's. What's this place? This is the 8th place. What is 8? 8 is 2 cubed, right? So that's why, so the units place has 3 places, 2 to the 0, 2 to the first, 2 squared. This has 3 places, 2 cubed, 2 to the 4th, 2 to the 5th, which is what I'm doing here with the other guy. Anyway, you have to take my word for it. You don't have to be confused. You're going to draw pictures and put boxes around them. Okay? So but I can't put it in my calculator because my calculator is only going to take 10 digits of binary. Unless I have a TI-89 calculator, then it'll take 16 digits. Yeah.
If it's this stinking confusing,
Isn't it great?
no.
Yeah, it is. It's
No,
wonderful.
It's like, I love playing with numbers,
Yeah.
but it's confusing as hell.
Yeah. Isn't it great?
So-
It won't be.
What is there, 2 people in the world that understood it?
Originally?
Yeah.
No, probably not. Probably more than that, yeah. Think of something that's really confusing. Think of the global GPS system, global positioning.
Okay.
Okay. How many people in the world do you think there are that understand it?
How many people can build a car?
You know,
An engine, I mean,
yeah, lots of people could, right?
no, I don't think so.
Yeah, lots of people can build a car, not by themselves, but with help. There are 7 people in the world that understand how the GPS system works. The rest of us use it. That's what we do. You know, so, and some of us don't even use it, right? But the rest of us I put it in my car and I tell it I want to go to Connecticut, and it takes me there, and I'm perfectly happy. I don't have to know how it works. I don't have to know that I need 7 satellites. I don't have to know that there's a time delay between them. I don't have to know anything at all. So at the beginning of that, before there was anything else, before you could have digital phones, before you could have your first computer, before you could do any of those things, George Boolean came along in 1820 and did Boolean algebra. Boolean algebra is something that is true or false. He was building on the Greeks. The Greeks had the same logic system of true and false from 3,000 years ago. He was building on that, but now he was giving it a mathematical construct. When the digital circuit people came along, just after World War II, basically, before and after, mainly after, they took that mathematical construct and put it into our electronics. But we fought World War II without any digital circuits. That didn't happen in the Gulf War. Those were all digital circuits. So when the Army guy picks up his radio and says, Bravo Charlie 35, I want a fire control mission at 33.4, what gets transmitted? It's not what he said. What he said gets transferred into a Fourier transform. The Fourier transform is modulated and sent out over multiple frequencies, hopping up and down, back and forth, so that it can't be interfered with to get to the receiver that takes it out of that frequency domain of information and turn it back into something that I can hear, and I hear exactly what the guy said. But how many people will understand that right away? Not very many. So it'll take me. All of you have something between those 2 ears of yours. What are they called? A brain, right? It has been wired for your entire life to think the way you currently think. Okay, which you're perfectly happy with. You're perfectly happy with the way you think, right? The sky is blue, the grass is green, perfectly happy with all that. Well, I'm here to tell you that we have to rewire it. It's going to take 2 years. And when I get done, I will have an electronic technician. I will have a robotic technician. Okay? Until then, there are things we have to go over to get there. There are things we have to get to. That's what I got to the first part of the class where I said, you need to learn something every day. Have you learned something today yet? Yeah, I learned my 8th grade math teacher really hosed me over when they didn't teach me all the math I'm supposed to know. I learned that my 10th grade math teacher, I should have paid more attention in 10th grade math. I learned that if I want to be an electronic engineer, I should start at age 20 instead of age 45 or whatever, right? Those things I know. But we have a Navy electrician in the room. When you went to BEE school, did you not cover this?
I was straight to the fleet.
Oh, you went straight to the
Yeah,
fleet.
that's
Ah,
right.
forget it. But the BEE school, well, the first thing they do, that's what's BEE anyway? Basic Electrical and Electronics School. You get right out of boot camp. They go over binary numbers. They go over octal numbers. They go over hexadecimal numbers, which we aren't at yet. Yeah. But remember that there's a calculator out there that's going to do this for you. These things are there. We have to use them. All right, so what do I have to do
How important
next?
is it going to be for us to understand binary?
Pretty important, yeah.
Because
Binary is 1 and 0.
I'm missing why there's one.
So we'll go back to binary. We'll go back to base 10. There's base 10. 1, 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I ran out of room. Binary. 0, 0, 0, 0. 1, 0, 0, 0, 1. Normally we don't write the beginning zeros, right? And normally. So if you had $1, you wouldn't write $1, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 1, right? You wouldn't, that'd be a funny way to write $1, you know. But in general, you wouldn't do that, right? You just, you know. But in binary, normally we write it 4 things at a time, and with the zeros there, 0, 0, 1, 0, 0, 0, 1, 1, 0,
There's a two,
1,
2
0,
and
0.
1 left over. Is that why it's 1, 1 for 3?
3 is a 2 and a 1 makes 3.
And 1 is remaining. You have 1, 2, and 1's remaining. That's why it's 1, 1.
Yeah. So you have 1, 2, and 1, 3 for 1, 1, and 1, 2, and a 3. I add them together, I get 3. 2 and 3 is, yeah, and this is the 4's place, so 1, 4. So I got a 4, and I have a 1 for 5. I have a 4 and a 2 for 6. I've got a 4, a 2, and a 1 for 7.
1, 0. Okay.
I got an 8.
I get it.
There's only one lousy 8. I got an 8. A 9 is an 8 and a 1. A 10 is an 8 and a 2. And I can continue that.
And the next one will be 16. The next time
Yeah.
you go to 5 digits at 16.
So I'll do it again. All right, so I got 11, 12, 13, 14, 15, 16. So I'll draw a line there so we know where we are. So 11. 11 would be 8 and 3 and 2 and 1. 8, 2 and 1 for 11. 8 and 4 for 12. 8, 4 and 1 for 13. 8, 4 and 2 for 14. 8, 4, 2, 1 for 15. 16, no 8s, no 4s, no 2s, no 1 for 16s. All right, and then I'm going to do it again. I'm going to do it in octal. Okay, so I got it 0, 1, 2, 3, 4, 5, 6, 7. I'm going to draw a line so that we know where we are. 8 is going to be 1 8 and a 0. 9 is going to be an 8 and a 1. 10 is a 8 and a 2.
Okay.
11 is an 8 and a 3. 12 is an 8 and a 4. 13, 8, and a 5. 14, 8, and a 6. 15, 8, and a 7. 16 is 2 8s. Okay, so that's what I'm doing.
Makes sense.
That's too bad. I'm sorry about that. I apologize. Yeah.
I
Shoulda-
just think
shoulda
just the
got-
binary part's like, it was confusing.
Well, it doesn't get confusing yet. Trust me. Yeah. It will get confusing tomorrow. I mean, not tomorrow, but the next day. Okay, so we have all of 10 minutes until we get to quit. Can we do the next guy? Why not? All right. So after we got sick and tired of writing things in octocode to make our computers go, and we did that. I used to have a robot. It's that I threw away maybe 20 years ago now. It was a Heathkit robot, and you programmed it in Octo. And we had it say, we programmed it one day to say, "Wake up, Charlie," or something like that. You know, some kid was always sleeping in the room, so we programmed the robot to 15 minutes in the class say, "Wake up, Charlie," and it was really fun. And then we threw it away because it was pain in the rear end. Well, the computer science guys got really tired of programming in decimal in binary real quick. So they went to Octo. They went from Octo to hexadecimal in about a year later. So they could program in hexadecimal, which allowed them to program 4 bits of binary at the same time, and they could do it quicker. Now we use our keyboards. That was before we had keyboards. So in hexadecimal, we have 0s, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, A's, B's, C, D, E's, and F's. Okay, so we have 16 numbers, 0 through F. Okay, so we're going to go back for a moment, and we're going to look at base 10 again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to go to binary. 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 11, 12, 13, 14, 15, 16, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0. Now we're going to look at that in octo. 0, 1, 2, 3, 4, 5, 6, 7, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, we're there, 1, 5, 1, 6, 1, 7, 2, 0. Then we're going to do it again in hex. If I could spell hexadecimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 1, 0. Okay, so my F is 1, 1, 1, 1. So when I program into my program logic controller, I plug in F, 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 F. I put that in there in hexadecimal. What does that mean? That means 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. It means 16 ones. That was the longer to put in if I had to do that. Okay. It means something different than that, and we'll get to that later. You don't want to get to that right now.
How can you have 4 Fs if after F you start at 1, 0?
Well-
1, 1 after that?
No,
Should
yeah,
be
after,
17?
yeah, well, the next 17 would be 1, 1, yes. So F would be 63, I think. Yeah, F would be 15,
And then you have to go another 15
And-
before you get to.
and double F would be 63, and triple F would be 255.
Double F would be 255.
Double F is 255?
Yeah.
Okay,
Because it's 16 squared minus 1.
yeah, okay. 255. And triple F would be, I think, is it 4090 something? Be easy enough to do.
46.
Yeah, 4096,
So that would be 4095.
4095, right? All right, but that's just one of those uninteresting things. All right, so now the issue is, I've got it. Yeah. So now the issue is I've got a number. Oh, I don't want that. And let's take a number. 2, 3, 5, 6. And it's in base 10. And I want to change it to hexadecimal. And how am I going to do that? Well, I'm going to take my calculator. And I'm going to go 2, 3, 5, 6. Second function base. Convert to decimal. And that was stupid. I just converted a decimal to decimal. That was cool. You saw it on my face, right? Second function base. We want to convert to hexadecimal. All right, so that's going to be a 934 in hexadecimal. Well, I don't necessarily have to use my calculator. I could take that number and I could divide it by 16. Okay, 2, 3, I can't do it in my head anymore. Divided by 16. Okay, so I get a 147 remainder 4. No, I don't. You know I didn't get that right. I got 147.25. Okay, the 0.25 was the remainder, which is be 1/4. 1/4 of 16 is 4, so my remainder is going to be 4. I divide the whole part of the number by 2. 147 divided by 16. Divided by 16, who put the 2 there? And I get a 9. Why would I get a 9? Oh, 9.1875. Well, what does that mean? Well, I'm going to subtract 9 from it, and I'm going to have 0.1875 times 16 gives me a 3. So this is a remainder of 3. I'm going to divide this by 16. 0, remainder 9. So there's my 9 my 3, and my 4. So I still need a calculator to divide by 16 because I can't do it in my head. So if I have a stupid calculator that doesn't change it directly to hexadecimal, I could do it that way. Okay, let's look at 2 minutes to go. 1 0 1 0 1 1 1 1 0 1 0 1 0 0 1. And the issue is, what is that in hexadecimal? Okay, so I make these guys, I group them in 4s this time.
Why are you grouping 4s?
The same reason I grouped in 3s last time when I went to octo. So it's the 4s that give me the hexadecimal. So think of zeros in front of those, and those are groups of 4. So that looks like a 4 and 1 is 5. That looks like a 7, 8. That's a 10 for an A. There's a 1 and a 9. 8 and 1 is 9. So that's going to be 5, 7, 8, 9. Okay. I want to take the same thing and I want to change it to hexadecimal, octo. So I group it in 3s. 5, 3, 6, 5, 1, base 8, hex. So I can group it in 3s and get octo. If I have binary, I can group it in whatever. So now I have that number and I want it to get it in base 10. Okay, I can't put this number in my calculator and get it in base 10. It's too big. But I can take the hexadecimal one and put it in my calculator and find out what it is in base 10. So I put in 5, 7. I got to change the base first. Base type. No, I don't. I put it in second. Okay, so I got 5, 7. Second function A, 9, second function base type hex, second function base change to decimal, and so in decimal I'm 2, 2, 4, 4, 1, base 10. And guess what we're doing 2 days from today? The same thing all over again. Because how many times do I have to say something before you're going to understand it? How many times?
So I understand it.
18. 18 times. Okay, so we got to go over on, off 17 more times. We have to do over base 10 17 more times. We have to, no, really. Yeah, that's what we got to do.
I think we can skip the on off.
Well, we can skip the on-off one, maybe.
I had a question.